In the last video, we took a look at uniformly accelerated motion, one dimension. We'd like to extend that into two dimensions. Now, to do that, we're going to have to build a little bit more machinery with regards to vectors. So let's start again with just some vector. Let's call it A. It does not matter what the vector represents, but if you want to think of it as a displacement, just to have something to hang your hat on, that's fine. Now, it turns out that we can make this vector up using two special vectors that are called component vectors. So one of the two vectors we will need will be a vector that points purely along the x-axis. There we go, ish. And this one will be called a sub x. And this is a vector in the x direction that goes as far to the right as our vector a would. And similarly, we can do the same kind of thing for up and down. We can have the vector that points purely in the y direction that we call a sub y. And this is just the vector that points up and down exactly as much as our vector a does. Now, if I add these two, here I'll just add them by the parallelogram rule. There we go. We see that a sub x plus a sub y will equal my vector a. So a sub x and a sub y with the little vector signs over them are known as the component vectors of a. You know, just like the components of a car. You know, you need 4 tires and stuff like that. You know, it's the same kind of deal here. These two vectors here are, if I put them together, they make the vector I'm interested in. And just to remind you of some notation, the magnitude of my vector A is usually just written as the letter A without the arrow over it. And this is always positive. It's just the length of the vector. Now, where things get a little weird in the notation, but this is very standard notation, is as opposed to component vectors, there are, and I'm really sorry for the horrible jargon here, vector components. So here I'm imagining, again, my vector A, like so. And my vector components would be basically like if I imagine my vector A is the hypotenuse of a triangle. This is AX and AY. And this AX and AY are not vectors. They are scalars. So the X component of our vector A is A sub X, but it could be either positive or negative. It's positive if it's pointing to the right, and negative if it's pointing, if it's pointing to the left. Unless you choose otherwise. But that's the default choice. Similarly, the Y component of our vector A is A sub Y. And again, it could be positive or negative. Positive means that the vector A points in the up-ish direction. And negative means the vector A points in the down-ish direction. So our vector component A sub X is the magnitude of the corresponding component vector except that we allow for the possibility that it could be positive or negative. Again, positive would mean that our vector A points right-ish, and negative means that our vector B points left-ish, and so forth. We're going to usually be more concerned about our vector components than we will the component vectors, but occasionally the component vectors might show up. But mostly the vector components are what we're going to care about. So we've been working so far just in magnitudes and directions. And so now we might need to find components for our vectors. So let's say this is my vector B. Let's say it's a displacement. Let's say its magnitude is 10 meters. While we're at it here, let's go ahead and say that we are directed at an angle of 37 degrees south of east, which is usually how physicists will talk about it. More on that in a second. And we'll label our components here bx and by, and we'd like to find the values of both of these. So while there are certainly exceptions to the practice, physicists tend to like to always dimension their angles so that they are never more than 90 degrees. This is different than, say, maybe in your high school trig class, where absolutely everything was measured counterclockwise from the positive x-axis. So if you had an angle of 280 degrees, that's what you had. Physicists tend to like to keep all the angles below 90. So to do that, for instance here, I'm specifying that my vector B pointed 37 degrees south of east. And so the of east bit is saying, okay, my reference is the plus x-axis, and then south is below that axis. I could have just as easily specified it over here. I could have said it was 53 degrees east of south. Either one would be fine. The reason that we like to do that has in part to do with technical issues of using calculators. When you use inverse trig functions especially, the manufacturer of the calculator has a problem. For instance, the arc sine of 1 could be 90 degrees, but it could be, say, 450 degrees. And so the manufacturer has to make assumptions about what quadrant the answer is going to be in. And turns out that the manufacturers have not made consistent assumptions, with the exception of quadrant 1. If you can keep everything in quadrant 1 in the calculator, so you can keep your angles between 0 and 90 degrees, all the trig functions are well behaved, pretty much regardless of who the manufacturer is. So that's the main reason why we like doing that. So what this means is, instead of, say, using sine and cosine being like y over r or x over r or things like that, usually we just rely on the old mnemonic SOHCAHTOA. So remember, that means sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. So here, let's say I'm trying to find my bx value. I know theta and I know my b. It's 10 meters. So I can say that so I want the adjacent. So I can say, all right, I have the hypotenuse, so cosine theta would be the adjacent over the hypotenuse, which is bx over by. So I can, bx over b. So I can multiply through by b to get that bx is b cosine theta. So that would be 10 meters cosine theta, cosine 37 degrees. And it turns out that 37 and 53 degrees are the interior angles of a 3, 4, 5 right triangle. So to one significant figure anyway, this works out to be plus 8 meters. Now I put in that plus sign by hand. I got that the length of this is 8 meters, but it's the fact that B points right-ish directs that I'm going to put in a plus sign. So let's go ahead and find by by the same logic here. So by, I'm looking for the opposite. So that would be a sine. So sine theta is opposite over hypotenuse. So there'll be by over b. And so by will equal b sine theta. So that will again be 10 meters sine 37 degrees. That would be 6 meters, but since you know it's pointing down, we go ahead and stick a minus sign in, just like we stuck a plus sign in there for it going to the right. Okay. Now, let's say you had the components and you wanted to find the angle. Well, let's go ahead and work that out. So if we have the components, so again, we'll just use the exact same vector b. So no surprise when we discover that'll be 10 meters long. And no surprise when we discover that we'll be at 37 degrees south of east. But we're going to note that bx is equal to 8 meters. I'm sorry, we don't officially know that that's 37 yet. There we go. So bx equals 8 meters, by equals -6 meters. Okay, so we can get b by using the Pythagorean theorem. We have the two legs of a right triangle. And so by the Pythagorean theorem, we know that b squared would equal bx squared plus by squared. So take square root of both sides. I get that b will be equal to the square root of bx squared plus by squared. And people are getting really fancy. What they say sometimes is that they're adding bx and by in quadrature, but I'll try to avoid being fancy like that. So b will be the square root of 8 meters squared plus -6 meters squared. Notice when I square it, the minus sign goes away, so we never had to stress about that. And sure enough, that works out to be 10 meters. Now here, since I have the components, what I have is I have the opposite and the adjacent. So that's going to mean that there's going to be a tangent coming up. So tangent of theta would be the opposite over the adjacent. So here the opposite, since by is negative, I'm going to stick in by hand a minus by, just to turn that into a +6 later when I put it in, over bx. Now what I have to do is take the arctangent of both sides, so theta will equal the arctangent. Remember, the notation for arctangent is tangent to the -1. You're not actually raising anything to the -1 power, it's just the notation that mathematicians use. It's the inverse operation of tangent. So tangent, you give it an angle, out pops a number. Arctangent is you give it a number, out pops the angle that would give that as a tangent. So this will be the arctangent of -by over bx. So my angle will be the arctangent of -6 meters. That's why I stuck in that minus sign by hand, over 8 meters. Now, when we're going in checking our units, when you have trig functions and especially inverse trig functions, the argument of the function jolly well better not have any units. So it's a good thing that the units of meters canceled here, because I don't know what the arctangent of meter would mean. I know what the arctangent of 0.75 means. The arctangent of 0.75 means 37 degrees. Now, this still isn't going to completely describe everything because we aren't making the default choice of counterclockwise off the plus x axis. We actually have to look at how this is pointing. It's pointing right-ish, and our angle is dimensioned off of something horizontal, so it'll be some direction of east. It'll either be north or south of east. And since we're pointing down-ish, it's south of east. Okay, so what's all that good for? Let's say that you want to do some vector arithmetic. It turns out that vector arithmetic in components is very straightforward to do. So let's say you have a displacement, and turns out that in physics we usually use r for position when it's in more than one dimension, and the x component would not be written as r sub x, but just as x. That's just kind of a special thing we do purely for position and also displacement. Similarly, the y component, you just write y instead of r sub y. But if you were to write r sub y, people would know what you mean. So let's say you have two displacements in a row. So somebody's walking first in one direction, then another, and we'd like to know what the net displacement was. Well, we can say, that the first displacement was -2, 1 meters. So this would mean that the person ended up 2 meters west of where they started and 1 meter north of where they started. Remember, with the displacement, that doesn't say anything about the path, it just says where they ended up relative to where they started. And let's say the next displacement in their journey that we observed was 4, 3 meters. So this would mean that they ended up 4 meters north and 3 meters east of where they started. And again, we're not going to say exactly how they got there. Now, if I want to know the net displacement, that's just going to be the sum of the two to get the final displacement. So that'll be the sum of delta R1 plus delta R2. So when you do this, we can just add things up slot-wise, it turns out. So we can say -2, 1 meters plus 3, 4 meters. And then what you do is you just add each slot up individually. So -2 plus 3 is 1. 1 plus 4 is 5. So my final displacement, delta R, is 1, 5 meters. So this 1 here, like I say, you'd think you'd be writing this as delta Rx, but we don't usually. We just call it delta X. And you would think that we would call this delta Ry, but we don't usually. It would be delta Y. And this is unique to positions and displacements. If it was velocities, we would indeed call it V sub X. Or if it was acceleration, we would indeed call it A sub Y or whatever. But this is just unique to displacements and positions. It's a little quirk of physics notation. So let's say you wanted to subtract. Let's say we want to find a displacement. Well, maybe you worked out that the initial position of something was located at 3, 2 meters. And the final position was at 4, 6 meters. delta r, the change in position, be r final minus r initial. And it's the same deal. You just subtract slot-wise. So you'll say 4, 6 meters minus 3, 2 meters gives me 1, 4 meters. All right. Let's also, while we're at it, say we know graphically we could also multiply by a scalar. How do we do that when it's in components? Well, let's say we have a vector, a velocity of that's -7, 9 meters per second. Now here we would legit call this v sub x, and we call that v sub y. Again, calling r sub x x and r sub y is unique purely to position and displacement vectors. Okay, so let's say we are told that something is going at twice the velocity of that. How would we find that? It turns out that scalar multiplication distributes across all the slots. So this would be 2 times -7, 9 meters per second. Well, 2 times -7 is -14, and 2 times 9 is 18 meters per second. So that would be the velocity of my thing going twice as fast. All right, just one last bit of notation. It turns out that in problems such as thinking about things going down ramps or hills, stuff like that, a lot of times we'll discover it'll be very convenient for us to choose our coordinate axes to be parallel and perpendicular to the ramp. So there we go. So say if we were thinking about a crate sliding down the ramp or something like that. For this kind of a problem, we'll discover very soon that it's be very convenient to say that this is the x-axis, that's the y-axis. So then if I were concerned about some random vector A, could be an acceleration, could be a velocity, could be a force, whatever. When I take the components, first off, you'll need to be very careful. You need to drop down to pick off the perpendicular. So this piece right here would be my a sub x. And again, dropping back, so this is perpendicular right there. This piece here would be my a sub y. Now, in a quirk of notation, a lot of physics texts will also say in these special cases, instead of referring to it as a sub x, they might call it a parallel, and this as a perpendicular. So a parallel means the axis that's parallel to the special surface we're worried about, and perpendicular means the axis that's perpendicular to the special axis that we're concerned about, which is probably usually x and y in that order, but doesn't have to be. All right, so with all of that in place, we'll go ahead and in the next video and extend our definitions of our kinematic variables to do things in 2 dimensions. Catch you in the next one.